So yes, I will be there, but I will be there. Sorry, I'll be there in the beginning tomorrow to help Kanichi administer the exam. We will be doing the exam in your lab during your lab class. If you wake up and you find you are atrociously sick, email me immediately, and that way we can find a time for you to make it up. Cause I don't want to get sick. So let's see. And finally, okay. So this should be the final piece of that, and then laptop HDMI. Yes, great. Okay. So documents, teaching, and that will be in data structures and practice one final. So first off, you may have noticed that the exam has 105 points on it. The exam. So because this is the first time going back to paper in a few years, I've included a 5-point buffer on the exam. So the exam is out of 100, but there's 105 points on the exam. Make sense? So in other words, you could get 5 points incorrect and still get 100 on the exam. So yes, technically it's possible to score over 100. At that point, though, you really don't have to worry about scoring more than 100. Okay. I'll put some on the exam. I will have some useful notes here as well. Like here's your string methods that you might find useful, like the starts with. Not everybody knows that there's a starts with method. And then these things over here. Things are never, the math is never, if it looks like the math is complicated, it's not. Don't leave questions blank because I can't give partial credit for blank answers. And let's see. So let's go ahead and get started with these. All right. There will be a question, at least a few questions like this on the actual exam, given a linked list, a doubly linked list. Please indicate which node is being referenced. So we look at D. We go D.previous.next. We end up with C. Right? Makes sense? Everybody follow that so far? That shouldn't have come up too much of a surprise. All right. C.next.prev.prev. So over here we've got C, right? C.next, and then two .prevs, .prev. There we go. And then this one, as long as you're not going out of bounds, you can cancel out the moves. And so we would need to do 3 nexts in a row without a prev to go out of bounds. So, and that doesn't happen here, right? Next, prev, next, prev, next, prev. So we can cancel them out. Next, prev, next, prev, and we just end up with B, right? Okay. All right, yes, so the answer for all those practice problems were B. Write a sequence of commands that will remove the tail of a doubly linked list, and then using a linked list with 3 nodes, draw what happens to the list as each line executes when you remove the tail. So in other words, these two things are conjoined, so let's go ahead and do them together. So I'm going to go ahead and make a doubly linked list. Okay. Draw what happens when you remove the tail. Okay. Here's head, here's tail. So the first thing we want to do to remove remove the tail of a doubly linked list. So what we want to do is we want to make sure that with the doubly linked list, we've got a bit more flexibility. We can say tail is equal to the thing before it, tail.prev, right? Tail is equal to tail.prev, boom. So now what's going to happen is that we would draw that tail is now this. Okay. Next step is we'd want to make sure that that tail doesn't point to this thing anymore. Okay. Tail dot next equals to null. We don't have to say tail.next is equal to head because we're not dealing with the circular linked list here. Also, I'm working in Java, so I suppose I should remember the semicolons. And that will get rid of this pointer over here. Now, if we want to be really clean about it, before we do that, before we get rid of that pointer, what we should do is we should, before we get rid of that pointer, this .next, we should get rid of this thing's .prev, right? We want to be really clean about it. So we can go ahead and do that. There's nothing wrong with either approach because the garbage collector should ideally come for the old tail. But we could do something like tail.next.prev equals to null. And that would remove this, and then that would remove, and then the third line would remove that. Sequence of commands that would add a new item to index 0, so new head, so boom. Right, assume we've got a node called adding. I'm not going to bother declaring it, but here's head. So adding, first thing we want to do when we're adding is attach the node. Adding.next is equal to head. So here what we do is we take the node and we attach it. Then we say we got to still connect it, so head dot prev is equal to tail, and then update the list to account for what's been changed. Head is equal to adding, and I'll update this node. These will be fairly straightforward on the exam. Yes?
Do you mean head.prev equals adding?
Head.preving is that. Good call, yes. Too much. I've been doing the circular linked list too much. Okay. All right. So in terms of difficulty on the exam, so you're going to have two problems that are like that would come out of lab 2. This one, much easier than what you would experience on the exam. This one, a bit harder than what you would experience on the exam. So it's the difficulty is somewhere in between those two. I highly recommend, by the way, that you review your problems from exam 2, especially the one with like the last one, the one that I would ask all of you about with removing items from the list. Okay? So this one, fairly straightforward. We can go ahead and just transition over to here. I'll put this in here for ArrayList. We're already in ArrayList exercises. Might as well use this. I don't need draw anymore, so I'm going to copy that. Okay, and then we're going to return. It's the difference between the max and the minimum, right? Or no, it's max plus minimum. So max plus min, so that was already there. So what we need to do here is go through. Now in Python, you just simply ask for the max and the minimum. That's no problem. And also the reason that integer.max value is used for minimum, and that is used because you've got, that's used because you've got, you know, the smallest thing in the list is probably going to be smaller than the biggest number you can store in an integer. And the reverse is true for max. Okay. So we can do for I, I'll do for each int I don't know why it lays it out like this. For each integer I in list, if min, you should be very familiar with this at this point. If min is less than if I is less than min equals I, and then same thing for over here. If I is greater than max, max is equal to I. Do I care about the do I care about the ties or whatnot? No. You if there's ties and I don't tell you how to handle them as you see fit. So the interesting question is the next part, which is what is the runtime of this algorithm? Okay? What's the runtime of this algorithm? Yes? O of n. Right. What if it's does it matter if it's a linked list or an array list in this case? No. Okay. So here's the other question, which is if I change it to this, int index is equal to 0, index is less than list dot size, just change it to the for loop we've been doing forever, and I say int I is equal to list dot get index. Okay, there we go. If I change it to this, and I ask you the same question, what's the runtime of this algorithm? Yes. O of n. Does it matter if it's a linked list or an array list? Yes. Yes, it does matter now if it's an array list or a linked list. Array list, this operation is constant time over here. Linked list, this operation is linked list, this operation is O of n. So it depends on your assumptions. So the answer to this is actually, we assume it's array lists. That's fine. I'm assuming that you're answering for array lists in this part. But if you feel like, oh, I've written something that's going to be different for both, and that does matter, feel free to mention that. It's an important thing to note that basically how you implement an algorithm does make a difference. Okay, so let's go ahead and look at this. So for doing the analysis in this case, let n be the number of strings. Assume that all strings have the same average number of characters, right? And so it takes an equivalent amount of time to work on any one string over any other. Or you can let n be equal to the number of characters, in which case you'll want to do the same analysis anyway. Okay. So reverse. So this one we are creating a new list with all the strings reversed. So I'm going to create a list of string called output over here. If you don't use generics on the exam, that's fine. But at this point, I just need to use generics here because if I don't, Java gets mad at me. And I don't like it when Java gets mad at me. So output. So now this time again we'll do a for each loop for string word in list. For each word in the list, we need to create the reverse of that word. Okay? Now there's a couple different ways to do that, depending on how well you know your Java and how deep down you've gone into that. First is just simply the manual way, which is string reversed is equal to the empty string, and then we say for, and now to iterate over, then we need to iterate over the string. For int I, so there's a couple different ways to do that. For int I is equal to 0, I is less than word.length. Okay, and then I++, and then we can do word.char@I, and reversed is equal to reversed plus that. So if we do that, that just simply gives me the same string, right? That gives me the same string. So if I did, this would give me nothing, then H, then E, then L, then L, then O for hello. But if I reverse the reversed statement and do it like this, I would get blank, then H, and then EH, and then LEH, and it would concatenate in reverse. So that's basically this is probably the most redundant way to do it. Similarly, you can do the same thing with the for each loop if you want to be, I find it to be quicker when you're typing with a for each loop on a computer. You can't do a for each loop on a string. What you need to do is then do, you got to use word.toCharacter array in order to do it on, to turn it into an array, so you can do a for each loop on it. I like to do that a lot, not on paper though. It's a pain on paper. However, the last thing I would like to note is that what we can do is we can do something along the lines of, if you know your Java, there's a string builder class, which is deprecated in favor of a new class. I don't remember what that one is, but we can do new. So we can do new string builder, and that gives me word. And now that creates a new string builder object. Now, why would I want this? First off, I can't store a string builder object in a string. What I can do, though, is I can do that, which is really weird, okay? So I'm just doing this to show you that you can do this in one line, and it's kind of weird, but it's useful to know. String builder does have a reverse method, which reverses with the contents of it. So and by the way, what string builder is used for is that concatenation is kind of an expensive operation. And so string builder is used if you want to do a lot of concatenations and then does all of them all at once. So string builder.reverse.toString, and there you go. So this turned it into a string builder object, called the string builders.reverse object, called it toString to convert it to a string, and there you go. Okay. Regardless of how you get your reversed word, okay, because I like to show, okay, here's an easy way and here's a way you can do it if you know a lot. Regardless of what you do, you can do, we need to do list.add, sorry, not list.add, but output.add. And then we want to do reversed. Okay, there we go. So that's another way. So that's one way to do that one. And again, it's not that long if you happen to know how Java works or know about string builder classes and stuff like that. But otherwise, you just have to do that manual, this annoying manual bit over here, which is just 2 lines of code plus a sorry about this. Let's see. Does that help? Okay. Yeah, sorry. I had to move it out of the way to open that. So, all right. So next, let's go ahead and get on to the next problem. Okay, time complexity. The time complexity statement is O of n no matter how you slice it with the way I've written it. It's either, so first off, you've got either n strings that you go through each one of them once, and you can assume that each string is going to be on average the same length, right? Otherwise, a more realistic way to look at it is n is the number of characters, and we've just broken the characters into chunks. But long story short, no matter how you break those characters up, we're just working with each character exactly once, right? Each character gets messed with exactly once. So it should be an O of n operation, assuming that this is a constant time operation, which it's not, but we can assume it is. Here it is, or it's a linear time operation, and that makes it nice. Okay, what is that? Why is there an error there? ToString. Excuse me. I assume I don't have. Oh yeah, there we go. Yes.
So something can only be an O of n squared operation if there's a nested for loop, but both of those for loops are going through the list itself.
Pretty much.
Okay.
Pretty much the same thing. When you're going over n by n entries, when basically for each item you're examining each other item.
Okay, but for each item, if you're examining that specific item,
It's going to be linear.
okay.
Mm-hmm.
All right, gotcha. Thank you.
Okay. Delete list. This is a pretty trick question, actually, which is why it's 3 points. There's a few different ways to do that. This one essentially, so making it empty, how can we do that? So first off, let's go ahead and make we have to first off, for my exam, I've got to make a new, let's call it a new Java class exam. Sorry, I'm going to call it my LL for the exam. Doesn't really matter. You could call it whatever you want, linked list. You can pretend you're actually working in the linked list class on the exam because your code doesn't have to compile on the exam. It just needs to make sense. Okay, so then we also need to create our, you're going to be working with your node object, private static class, node, my linked list of e's. And then E item, E node, E next, and then public node constructor, node E item, because we don't want an empty node essentially. This dot item is equal to item. Excellent. Okay. So, and then this also needs three things. It needs I'm going to say access to the head. So node E head, node E tail, and then int size. A delete list would work something like this, by the way. I'm going to go ahead and write it on paper, on the paper though. We'll need this for the next part. So delete list, what do we need? So there's a couple different ways to do this. The easiest way is while head is not equal to null, this dot remove 0. This is why it would be a 3-point problem, because there's kind of a trivial answer for it. But what if you needed to do it manually? What if I said you don't have access to the remove method? In which case you need to, we got to actually work with the nodes, which is annoying. So what we would do is say, we do the same loop though. While, what I would do in this case is while head.next is not equal to null. So for these problems where you're working through where you're basically been iterating over everything in the list, you either want you either want to check while the thing I'm on is not equal to null, or while the next thing is not equal to null. And that's basically whether or not you have to clean up after yourself. So head.next. Okay, so while there's not an item, while there's still an item after me, while the next thing is not null, what I do at that point is I say head, okay, why can't I draw A's today? Okay, head is equal to head.next. I'm not going to worry about messing with the size because I'm just going to set the size to 0 at the end. So while the head.next is not equal to null, head is equal to head.next. Once the head is equal to null, once the head.next is equal to null, that's the only thing left in the list, right? So at that point, we would just simply say head equals null at that point, tail equals null, and size equals 0. Okay, nothing too scary there. Count, again, is another fairly straightforward method. I'll actually type this one in. So given a write an instance method called count, iterates over a linked list and returns the number of times an item occurs in the list. Okay, so the way these ones work is that you need to have is just like getNode, we are going to use a current to keep track of where we are in the list. And then we're going to also have an int count. Can we do that? Yes, because it can tell whether. Let's go with yeah, count is equal to 0. Can we do that? Java, you're amazing. I can have a count here and a count there, and you know the difference. Return count. Python's a bit less happy about that. And by a bit, I mean you can do it, just won't do what you want necessarily all the time. So count is equal to e.item. Sorry, not e.item. So we want to count some item. So we're going to set up a node e head. Sorry, node e current is equal to this dot head. Right? You can say head, this dot head. It doesn't matter in this context. And what we're going to do is we're going to say while. So we're going to go through the entire loop. How are we going to know when we're done going through everything? While current is not equal to null in this case. Once current is equal to null, what we'll do is that we'll look at the current item we're at, and then we'll move to the next one. And if we happen to move on top of a null, that means we just moved off the tail, which means we're done. Make sense? So we're going to say while current is not equal to null, and then we're going to advance it. Current is equal to current dot next. You could technically do this as a for loop, but that's weird. So what you do is you'd basically say int I, and then you'd have I is less than. You would just basically have current is equal to current dot next in like in the postfix, the post area. So what we do is that we simply say at this point if current is equal to current dot item is equal to the item that I'm looking for. And let's do it dot equals because that's the correct way to do it in Java. Dot equals item count plus plus. A very straightforward algorithm. No tricks over here. This takes O of n time because you're just moving through one item at a time. Make sense? In terms of Big O, there's going to be two types of questions on the exam. Three types of questions on the exam. The first one is the last thing on the test, which I already told you about, which was the analysis question, right? That one you want to use Big O for. Then there's the list items that you've already seen, the list methods, which is give me the runtime of what you just wrote. Okay? Not too scary. And then the third one is going to be where I give you some problems, like this one or this one. Let's merge. Where's the add method? I want to do the add method first. Yeah. So yeah, this one or this one that says, hey, we have, there's the, like your solution must run in O of n time. And what I did is I wrote on the program where any time I have like a restriction like that, I say you may break this rule for X points. So if you can't figure out a solution without breaking the rule, then you can break that rule. You'll just take a penalty. Okay. So very straightforward algorithm. While current is not equal to null, current.am. I plan on uploading this as soon as I'm done with the lecture, by the way, like before I leave the room. So if you're scrambling to keep it down, don't worry about or to write this down, don't worry about this. Write a static method that takes two sorted linked lists. Okay, so these are linked lists. That makes sense. So two sorted linked lists of integers and merges them into one sorted linked list and returns it. Since this is a static method outside of linked list, you cannot access the nodes. You're allowed to remove items from list A and list B. That's important. I'll mention whether or not you can remove items or not. In this one, we can, and we will do so. That makes it a lot easier for us to do. This is part of merge sort, and honestly, I love this algorithm. It's a very clever algorithm. And the way this works in O of n time is that it takes advantage of the fact that both of these, first off, removing an item from the head is constant time. And then if you have two sorted linked lists, it takes O of n time to merge them. Or two sorted lists in general takes O of n time to merge them. And that takes advantage of the fact that they're sorted. And the way that works, just to draw for a second, is that if I have 1, 3, let's go 2, 5, 4, 6, 8, 7. Okay, so I've got these two lists and I want to merge them together. They're sorted. What I can do is I can compare the heads to each other. I can compare 1 to 2 and 2 to 1, and I say which one is smaller. Because since I know they're small, and the reason I do that is because if the head of this list over here is smaller than everything else over here, then smaller than the beginning of that, because it's sorted, it's smaller than everything else in this, right? Because 1 is smaller than 2, it's obviously got to be smaller than 5, 6, and 7 as well, right? It's because this is sorted. This is guaranteed to be the smallest thing in the list. So by doing one comparison, I know that one item is smaller than all the other ones. And I already know this item is smaller than everything else because it's in its own list because it's sorted. So the way this works is I compare the heads. 1 compared to 2. Okay, let's go. I'm going to add 9 and 10 over here just to add to my algorithm. So 1 compared to 2, 1 is smaller. 2 compared to 3, 2 is smaller. 3 compared to 5, 3 is smaller. 4 compared to 5, 4 is smaller than 5. 5 compared to 8. 6 compared to 8. 7 compared to 8. Right? We just kept looking at the head of the list, and what I would do is I would remove them and add them to our output. Now notice that one of our things is empty. So in this case, we're done with comparing, and all we have to do is we can just simply take this and move it all over here to the end. Just tack it on to the end. Okay. So what we need, so first things first, we need an output. We'll do linked list. Right here I'm using a linked list rather than my linked list. So linked list integer. Okay. And now we're going to do, what's it called? Right, so output is equal to new linked list. Return output. Okay. And now what we do is we're going to use, again, a while loop. You got to get used to using the while loops for these indeterminate kind of things where you don't know how long they're going to run for. So while list a dot size is not equal to 0, and not or here, list b dot size is not equal to 0. Okay. Oh, forgot the 0. Okay. So this wants to run while both of those are not equal to 0 because if it's an or, well, one of them is always going to be above 0, so it would be an infinite loop and you'd get yourself into trouble. Okay, so all we have to do is compare the two heads to each other. So if list a dot get 0, and they're integers, so we'll just simply do less than, list b dot get 0, if it's smaller than that. Okay, else. So if it's smaller than that, list a dot remove 0. And so if the a is smaller, we're going to say we're going to remove it from a. But we got to remember we want to store it in our output so we can get an output. So we'd say output, well, look at me just jumping the gun there. Output.add. Output.add. So we remove the head and add it into our output. Otherwise, I simply copy paste this line, which you can't do on the exam, unfortunately. Although if you wrote ... if you simply if you wrote something like this, if you wrote same but list B, yeah, I'd take that. Because you know what I mean. It's again, you're on paper. You're allowed to do things like that on paper. It's the same, but as above. As long as it's unambiguous there, you know, yeah, or fairly unambiguous. Okay, so what if they're equal though? The answer again is that basically we kind of already coded that in. If they were equal, we would consider this one, the one on over here on list B, to be smaller. If we wanted the one on list A to be smaller, if they were equal, we just put less than or equal over here, right? It doesn't really matter. It's not something to worry about. Some students do though. Okay, so this will go until one of them is done. Now at this point, when we're done with the loop, one of them is empty and one of them is not. We don't know which one. Now there's two ways you could go about this. First way is that you write a for loop that runs equal to the number of items in the list and removes it. Like you do something like for I is less than, while. Now we wouldn't do it as a for loop. We'd do it as a while loop because that would make it easier. While. I'm going to erase this, by the way, because it's silly. List A.size is greater than 0. We would do something like this. Output dot add list A dot, what we had already done. Okay, but this is silly. Because we'd copy the same thing for list B, it would work. There's actually nothing wrong with it, but it's silly when you have a one line that will do the exact same thing, which is list A. That's what you want to do if you want to make sure you remove everything. If you don't care if you remove everything, you can just simply do output dot add all. Add all is great. Add all list A. If it's empty, it's not going to add anything, right? Output.add all list B. And then if you really want to make sure they're empty, list A dot clear and list B dot clear, right? If you really want to make sure they're empty. Yeah, those methods you may not know about. That's okay. I'm showing them to you because I like to show things like what if you don't have access to special methods and what if you do. You know? Might be worth looking through the documentation though for some of the problems. But if you don't, not to worry, because I put the relevant one. I didn't put add all there, but a lot of times I do. But I do put the relevant methods that you need to succeed over there. Okay. So let's see. And again, this takes oven time. Reverse we'll come back to later, okay? That will be our last problem. Here I'm gonna go and now take this and I'm gonna refactor this file from my linked list to sorted linked list because refactor, rename file, sorted. Okay. So, as I mentioned last time, for those of you keeping track, the problem we just did was all about linked lists that just happen to be sorted, and this one happens to go over a class called sorted linked lists. This is what we call hint. So, all right, rules, sorted linked lists. Sorted linked list, you add it, but you don't get to tell it where it is because it's a sorted linked list. It's going to figure out where it goes. Make sense? So if you add a 4, so if you got this list 1, 2, 5, you add a 4 to it, it's going to become 1, 2, 4, 5 because, again, you don't decide where the 4 goes. It's going in numerical order. Okay. As a result, we don't provide an index as sorted linked list figures out where the item should be. We want to write an add method. You want to use you can use either a singly or doubly linked list. We're going to use a singly because why make more work for ourselves? That just means, though, that we have to be careful as we add things, right? You can use less than, greater than, or equal to compare items, but if you remember how to use compare to, you can do so for extra credit. The less than, greater than, or equal to is good for integers, and I think I'm going to do it that way. Just simply change this to it's already E, so I might as well do compare to, right? So if you remember, compare to gives you a negative number, a positive number, or a 0. If you get a negative number for A dot compare to B, it means A is less than B. So we will, and I'll go to that as we get there. You can't use the add method because that would be silly, right? You can't use the add to index because that's kind of what we're writing. And you cannot use the get node class, although you can feel free to rewrite it. But we don't really need it. Okay. So public static, not public static, but public void add E item. Okay. If you want, we can go ahead and say, let's see. Yeah, we can refactor this into it. Do you want me to just deal with integers right now, or do you want me to do the compare to for?
On the exam, if we did if we acted like they were integers, would we get points off?
No.
Okay.
No. I said you could use less than or greater than.
Okay.
So I'm going to switch it to integer so that the program. I'm going to switch it to that way so that we know that it is going to work. It's going to be too much effort to refactor it. Okay, let's just keep going. Okay, so first things first, we want to give ourselves a head, or we want to give ourselves a marker to the head. We know that much. We need to have some kind of marker to the head, and we also need to have a node item, node adding is equal to new. And finally, this is what I was talking about. I'm going to modify this so that my code actually compiles, so that I have access to the compare to method. Okay. See, now you know why I say that it goes quicker on paper, because you don't have to worry about any of that kind of nonsense on paper. You can just get coding. Okay. So there's a couple cases that we need to think about. First off, but again, it kind of comes down to what we care about if we're modifying a linked list in general, which is, are we modifying the head? Are we modifying the tail? Are we modifying anything else? Okay, so let's look at, so how would I know if I'm changing the head? What needs to happen for me to change the head in a linked list that looks like this? So let's go with 7, 8, 15. Okay, so that's my linked list. What kind of number do I need to put in order for the head to change? Something less than 7. Which would mean it's something less than everything else in the list. Let's say 2. So that's one. So that's a case right there, which is if item is less than head dot item, or in this case, the way we would write that with compare to. Okay. So I will comment that out so you can see that there. If item dot compare to head dot item is less than 0. That's how I would tell if it was a negative item. Make sense? So that's the compare to function, right? If it gives me a negative number, this means that A compared to B. If I get a negative number, then A comes before B. A is less than B. So if I get 0, they're equal, and if I get anything else, they're going to be. If I get anything, and if I get greater, then it's going to be greater. So let's go ahead and actually let's simplify this. If it's less than or equal to 0, that even greatly simplifies it, right? If it's the same number, we might as well change the head. That's an easy enough thing to do. Okay. What we're going to do over here then is we are going to say adding, then it's just standard linked list stuff over here. Adding.next is equal to head. head is equal to adding. We are done here. Yes?
What's the difference between using compare to and using item, like what does it, did I see the code that physically would never, why would you use compare to over the non?
Compare to would work on things that are other than integers,
Oh, okay.
because you can use them on strings in that case.
Oh, okay. So you use it on integers and strings.
You can use it on integers, strings, or anything that's comparable to each other. Anything that can be sorted.
Okay, thank you.
That's a good question. Now, we also need to do, so we have an else statement. And then, let's see, should we do, let's assume we're worrying about the tail. So we can, but we'll worry about the tail later. So else, what we're going to do is we're going to say, move this over here because we only need current in here. Current.next is equal to head. And then while current dot next, and then you have to, then what we need to do is we need to figure out what is it going to be not equal to. Is it going to be current? Sorry. So we've got current not equal to null. We have to decide between two choices for when we're advancing. Either it's current is not equal to null or current dot next is not equal to null. So in order to do this, we got to kind of assume of how we're going to add things. So let's say I want to add the number 9 to this list, right? So first thing I'd want to do is check this against 2, right? Okay, so I'd check this against our base case. This is false. 9 is less than, no, sorry, 9 is greater than 2. So in that case, what I'd do is I'd check 9 over here. Now here's the trick. So if I'm starting out at the beginning, then current is equal to head, right? So that would be, this would be current dot next over here. This would be the dot next. And what I would want to do is I'd want to check if this item 9 is less than current dot next dot item, right? Do I fit between the two items? If I do, great. Otherwise, move on to this being current. And does this fit between current and current dot next? No, it does not. Move on. Does this fit between the two items? Yes, it does. So in this case, I would attach my item, and then I would have current dot next point to here, and then I'd be done. Okay. Now let's go ahead and assume, though, that instead of adding 9, I'm adding 20. I'd move this. Current dot next would be, in that case, equal to null. In which case I wouldn't be able to successfully add it. So we'll burn that bridge when we get to it. So, but for right now, the current dot next is equal to null. So let's see. While current dot next is equal to null, what we'll do is we'll do exactly that. This is our advanced statement. While current dot next is equal to null, if current dot next dot item, that's the item we want to compare to. So I'll do, and I often compare to dot x dot item. So item dot compare to current dot next dot item is less than 0. So again, if we're less than the item to the right of where we are, in other words, we know we're going to be above, so we know we're going to be greater than current. Because of this statement, our base case here, we know we're going to be greater than current, because we'll be advancing each time if we are less than current dot next. Sorry, if we're greater than current dot next, we'll be advancing each time, so we know we're going to be greater than current. So if that's the case, if this is true, then we know that we fit in between them. So we would go adding dot next is equal to current dot next to hook it up, right? I'd say in this case 9 is adding. In this case, I'd say adding dot next is equal to this would be current in that case. Current dot next and then I'd say current dot next is equal to adding. And then then we want to make sure this would stop. So you'd either want to use a break statement to stop it, or in my case, because again we're using a while loop over here, we should probably do a. I'll do a, because of the way I like to do things, Boolean done is equal to false. False. Well, that's not true, and not done. Done is equal to true. So once done flips to true, this entire thing will stop. Make sense? And now, so this actually will work, except if it's greater than all the other items. So in this case, we can assume that if we need a tail, we can just simply, so in this case, let's assume that we keep track of the tail to make it easy for us, right? If we don't, we would just simply, if you didn't keep track of the tail, you would just have a statement, if done is still equal to false, just add it onto the end, right? But in this case, we can just do this, else if tail dot item, so dot compare to item. So if the tail is less than the item that we're adding. If tail is less than the item we're adding, then then we want to connect it. Tail dot next is equal to adding. Tail is equal to adding. If I were to be it's okay. And that's it. That's basically right. Is it less than the head? Is it? Let's do this. And yes, let's go ahead and make sure that's a less than or equal to, then just make it short. And where's no current equal to head? Oh. Else. Why did that? Okay, there we go. I don't know what happened there. Okay. So let's just go ahead and so we've got modifying the head, modifying the tail, and modifying the body, right? Now, how many points did I say this one was worth? 15? Sure. If that was the case, I would probably say 3 points here. I'd probably put 3 points here, 3 points here, and then the rest would be here in this one, rather than splitting it evenly. Or it might be a 4, 4, and 8, because honestly, that makes sense. This is twice as important as those parts. You know. Yes.
This is kind of not like the question. Since we're handwriting it, we like to miss brackets or like semicolons. That's not going to affect us.
Not really. No. I might circle it. Or write it in, and I mean, as long as things are, that's also why you want to also indent things if you can. That way I don't have to guess what's inside the loop versus what's outside the loop. So if it's indented, I can tell, oh, that's supposed to be inside the loop. They just forgot their bracket. That's going to be a point, half a point.
Okay.
I'm not going to, but if it's completely ambiguous, then I'm going to have issues. And that might be a bit more, right? So be sure to indent as well. Yes.
How much of the extra credit you would
Probably 1 or 2 points, depending. Okay. Now, let's go ahead. We've got 20 minutes left. So, I'll go back to reverse in a minute. Yes?
If we mess up the code for a question, but it's a big O question, and we get the time complexity of it right, do we get the points for that?
The big O is more of avoiding a penalty.
Okay.
So, I mean, if you're referring to like this,
Yeah.
yes, you get the points for
Okay.
that. Okay. Let me go over this part because this part is, as I mentioned, going to be on the exam, so you should know it. And the day that I get everybody in the class, that everybody in the class gets at least 16 points on this one, is the day I'll stop asking it. So you can thank your predecessor's sacrifice then for this question. All right, so we're going to compare them in 3 ways. We're going to compare them in terms of memory usage, adding and removing, and we're going to compare them in terms of get and set. We'll go in reverse order because honestly, get and set is the easiest. Adding and removing is the hardest, but it's familiar. Memory is unfamiliar to you. So get and set is fairly straightforward, right? Array lists for get and set and linked lists for get and set, right? You'll want to write more than what I'm writing down, obviously, here, but the point being is that array lists for get and set methods, array lists work in constant time. Linked lists, if they're not working on the head, it's going to be O of n time, right? Where n is the index. N is the index basically, because you have to iterate through n items in order to get to the item, right? For a linked list, you have to iterate, start at the head or the tail, and if it's a doubly linked list, you're starting at the tail possibly and trying to find the item in there. It's very bad. Linked lists are very bad at finding an item at a specific index. Linked lists, on the other hand, array lists, on the other hand, that's what they're great at. Given an index, you can just grab the item from that index because it uses the formulas that arrays do to do memory lookups. All arrays which array lists use in programming languages basically work like this, that if you given an index, if you have some item called, if you have some array called R, and you're storing array in there, what's going to be stored in there is a memory location of the start of that array. It doesn't store the entire array in that variable, it just stores the memory location at the beginning of that array. So the way you get to a specific memory location of an item is you go target is equal to the starting point of the memory address plus the index you're looking for times size of item, where item is the things which the item is. All the things that are being stored in the array list are actually going to be the same size, not just because of generics, but because if you're storing an object in there, you're going to be storing a memory location in there, so they're all going to be 32 bits. So start plus, but notice that is just simply a multiplication operation plus an addition operation, so it's constant time. Okay, so array lists definitely win there because it's always constant time. Okay. Next, for array lists versus linked lists, gets and sets. I'm going to start with linked lists because those are simpler. Okay. For linked lists, basically you have 2 different cases, just like you did, but now it's even more important. Head and tail. Manipulating the head and tail of a linked list is constant time, right? Adding to the head, removing to the head, that's just adding to the head, removing the head, adding the tail, removing the tail. That's just manipulating some pointers, right? Doesn't matter how big the array list is, if you're modifying the head or tail, no problem. On the other hand, if you're doing something in the middle, right? And again, you'll want to write this in more detail. You'll have to explain why. So I write this in more detail than what I'm writing down. If you write down this chart, I won't be able to give you full credit because you're not telling me why. The middle is O of n time. Why? Because we need to find the item. We have to find the index that we are about to insert our item or remove it from. Okay. Array lists, we need to actually classify a bit differently. Front, middle, end. Front, always O of n because you've got to shift all the items over. Middle is also going to be O of n because you have to shift n over 2 items over, half the items over. right? And then finally, if you're manipulating the end, this is where a lot of students lose points. So don't forget to write this out, please. Okay. It's constant time, except, right? Adding to the end of an array list is constant time because you don't have to shift any items over, except if the array list is full. Okay. If the array list is full, in that case, the star is O of n if reallocating, right? That's what you need to do for full credit. You have to mention that you're reallocating, that the list has to be reallocated, right? If it's full, you reallocate. Otherwise, it's constant time, right? So unfortunately, you do have this kind of, with array lists, you do have this unfortunate kind of thing where it's O of n, except when it's constant time because you're adding to the end, except if you have to reallocate, in which case it's linear time again. So, yes?
If you have to add, if you have to reallocate for front and middle though, wouldn't it be O of n squared because you have
No,
to shift everything
it's
over?
n and n. It's you.
Oh.
It's and if you have to, it would be you'd reallocate. So that's an n operation, and then you'd shift over those n items, which is another O of n operation.
So it's 2n.
Although if it was going to be smart, it would just simply move the item you're adding in first into the middle, and then. But that would require optimization that I'm too lazy to do for this class. Yes.
So just double checking, we don't have to mention anything about memory?
Memory is what we're going to do next.
Okay.
Memory is what we're going to about to compare. So yeah. Okay. So here it depends. If you're adding head to head or tail, linked lists are better. If you're just adding to the end, an array list is probably better, except for the fact that you have to reallocate every so often. But as we'll discuss in a bit, reallocation can be worked around. So when we're talking about memory, okay, with array lists versus linked lists, when we're talking about memory, array lists, we want to talk. So first off, we just need to talk about the overhead essentially. Array lists don't really have overhead, right? With an array, right? Each of these is going to be a pointer to the actual object being stored, which is 32 bits. That's 4 bytes. That's nothing, right? Same thing with a node. A node itself has, well, we'll discuss this in a bit. It also has a pointer to the item, right? Which is also 4 bytes. Okay. So that's 4 bytes because these point to the item. Now, linked list also has a next pointer, right? Which points to the next thing in the linked list. That's also another 4 bytes. Okay? And then if we're doing a proper linked list, we'll also have a previous pointer, right? Which will also be 4 bytes. So it uses 3 times the amount of overhead as an array list can. Okay? 3 times the amount of overhead. But that's not the end of the story because none of the space in a linked list is wasted ever. Right? All that space is being used. All those pointers are being used. In an array list, it's just possible that these things are only these things are filled, and then this space is wasted space. With an array list, you can have wasted and unused space. Remember, how much space can be unused? I mean, yeah, assuming that you start with a standard empty list and you're reallocating every so often, the largest amount of wasted space you're going to get is this is full. Then I immediately reallocate. And then the amount of wasted space you're going to get is this. And yeah, that's just going to be unused space. It's actually might be less bytes it's wasted space. It's just straight up wasted. Now there's ways around that. You can set the capacity of the array list in advance. You can actually do that in Java. There's also a .trim method, which is really useful for keeping your array lists just nice and memory efficient. List Java. let me go ahead and okay. Yeah, it's Java 8. Let's see. Array list clear removes everything. Ensure capacity. Okay, that says in advance basically says let's grow it to this size in advance so we don't have to reallocate. Make sense? If you know you're only going to have a maximum of 10,000 items and you're probably going to get close to that maximum, you might as well grow it in advance, right? So you don't have to worry about reallocating every so often. You're just all your add methods are going to be instantaneous. Similarly, if you got all this empty space at the end, let's see, it's trim to size, my bad, not trim, but trim to size. Your IDE will pick up on that, whatever, okay? Trims the capacity of this array list to match the list current size, right? So it says, let's just go ahead and do like the reverse of the reallocate. Okay. So a question from that I was so I'm going to ask you a question I was sorely tempted to ask on the exam. In fact, I asked it on last semester's exam, which is, why don't we reallocate the other way if we remove so many items, right? If we remove so many items, why don't we just simply shrink it down every so often, right? Say we're using only, say we use less than half, shrink it down to being to half the current capacity as opposed to doubling it. Right? We only grow the capacity of the array list. Why don't we shrink the capacity as well? Any takers on that one? Like I said, it was a question on last year's exam. Give me a good indication that I should add it to next year's exam, though. Yes.
Could it be something like you might be adding stuff like after that in memory, so that either way it's going to be wasted?
You're very close to the answer, but yes, you can. Once you shrink it down, you can add stuff again. You might add stuff again. In fact, think about and the key is think about what happens is that okay, if you say if I'm at full capacity plus 1, I need to double it. If I'm half capacity, I need to shrink it. Half capacity minus 1, I need to shrink it. So you could get into a loop where you're adding 1 or 2 items. You double, and every item, and now every operate, so you add 2 items, oh, now it's a reallocate. Subtract 2 items, oh, now I reallocate. So now every other item you're adding becomes an O of n operation on top of whatever you're doing. And that's basically what it is. I'd say if you wrote an array list to like to automatically manage memory, you might want to do it when you were at a quarter of capacity. But that's part of the reason why when we're just writing the array list, we just simply grow the capacity of the array list because it's probably not going to shrink down. All right. Yes?
Could you explain why the linked list is 3 times like more memory?
It's 3 times the overhead, I would say, not 3 times more memory. Overhead, because you've got these pointers, right? Each of these pointers is 4 bytes. Each array list, each slot in the array list also holds 4 bytes, right? It's not actually holding the item you're storing, it's holding a reference to the item you're storing. So this is the reference to the item, this is the reference to the item, there you go. So that's where they match up there. So each slot uses 4 bytes. And we're going to assume also that everything in the array list is filled up and there's no wasted space in the array list for a second. Okay, make sense? So 4 bytes over here, 4 bytes over here. That's fine. Where we get our issue is, and I'll draw it over here. Again, our node class has the item reference, right? That's 4 bytes. Every arrow is going to be 4 bytes. Then you have the next, and then you have the previous. So that's 4, 4, and 4 over there, right? Whereas you only have 1 4 over here. Make sense? You don't need a next and a previous for the array list. Make sense?
Yeah, but it's still going to be smaller, right? In memory.
Well, we're assuming here that this is filled up,
Okay.
right? And that there's no wasted space. And then if there's wasted space, it becomes, at the end of the day, both of these things are going to use O of n extra space in some way, where they're going to use a linear amount of wasted space or overhead. And they're going to be roughly equal in terms of use. If you're now, mind you, if you're going to be manually managing the array list to make sure that it is on point, the array list is going to be more efficient in terms of memory, because you're just essentially wrapping around an array and it doesn't get more memory efficient than an array does. Linked list, though, does have that extra overhead, but with the extra overhead comes convenience. And it's not nearly going to be and neither of these are nearly as bad as hash maps or hash sets, which we'll get to in the array list, where wasting memory is a feature, not a bug. It's a feature to make sure that our run times are acceptable. Because if we don't if we don't sacrifice our memory, the gods of runtime will be angry, and they'll punish us with linear lookup times for everything. So let's see. The remove method. So now this last method, since we only have 5 minutes left, the reverse method. All right, how would you reverse a doubly linked list? So I'm going to just simply walk through the various answers, and I highly, highly, highly recommend looking this one up on your own, because it's an interview question. Highly, highly, highly recommend. Hint, hint, nudge, nudge, wink, wink. Okay? So look this one up on your own. But what it is that the reverse method is so first off, the general way to think about it is, okay, I'll just add it in reverse to another linked list, and then I'll output it, and I've got myself a reverse linked list, right? So then the next step is, what if you don't have a reversed linked list? Sorry, what if you don't have a secondary list? In which case, the answer kind of becomes, well, I've got this doubly linked list, right? And what I'll do is I'll store I'll keep track of the head and tail, so I don't really mess it up. But let's go ahead and see how that would work. We'd want to go and say, okay, here's my current. And what I want to do is I'd want to say, okay, I want to take current.next. So this guy's current.next. Sorry, this guy's previous should become the next, right? And then I'd have to make myself move over here, but that makes that a bit of a pain. So what? Did anybody solve this one? Yeah. Anyone come up with a solution for this one?
Could you make like a new list and then just add the end?
Yes, you can make a new list. I'm saying, but what if we want to do this in place?
I don't know.
You don't want it. All right. So let's, instead of assuming that we're at the head or tail, let's just assume we're over here. We want to make sure that everything basically gets properly transformed. So we want to make sure that so this one, let's see. So it's just a matter of doing these in the right order. Make sense? Yes. The what? You could, the head and tail? Yes, that's what we have to do. That's what we have to do. We have to swap the heads and tail, the previous and next in this one. That's what we have to do. We have to swap the previouses and the nexts. So here we would say basically tail.previous is equal to, so tail.previous is equal, so current.previous, next is equal to previous. So next is equal to previous. This needs to point there as well. So now my previous points there. So the bombs are going to be the previouses. Dot next is going to point to, aha, okay. So what I need to do is I have to say dot. So what I do is I'm going to keep track of a current, a before, and an after. Right, that's all I have to do. Keep track of a current, before, and after. Okay, And for each of them, I simply would say, okay, it doesn't matter how where these end up, because I've kept track of current before and after. So I just simply say for each of these, I'd say current.next is equal to, current.next is equal to before, and current.previous is equal to after. Make sense? And then I'd simply set current is equal to after at that point and do it for every single one of them. Make sense? So all you have to do is keep track of current, before, and after. Right, makes sense? And then you just move forward like that. Did I lose everybody there or no? Okay. So now the last thing, since we're out of time, the last thing I'll leave you with is the final point of that interview question, which is, what if it's just a singly linked list and you want to reverse it in place? So you don't have any previouss to work with. Now it seems terrible, but notice that when I went over here, I didn't bother actually using any of the previouss. I just created some temporary variables. So the key to that one is creating some temporary variables. I would look it up. It's actually a fairly elegant solution. It takes linear time. You just move through it, creating a bunch of I think you need 3 temporary variables, just like I did. But you just simply advance forward and have this one point to here, right? You start out with current. You say for every current, I'm going to have current.next point to before, and I'm going to advance to the after, which I kept track of before I manipulated any of the pointers. That's how that one works. You just got to have these rolling kind of pointers. So again, I would look up a formal solution to that problem. It's a very cool one.